Welcome students to the momentum portion of our conservation of energy and momentum unit. We're going to be looking at the momentum equation and what gives objects their momentum or takes it away. The essential question is, what are the relationships that contribute to the momentum of moving objects? So let's talk about how we assign momentum or analyze momentum. So the first thing you need to know is that all objects that have mass and are moving have momentum. And the symbol for momentum is incredibly obvious. It's P, probably because M was already assigned for mass, and so they decided that it was going to be P. And the units for momentum are kilograms meters per second, which is pretty large, but it will make sense as we build the equation for momentum together. So we're going to look at some objects that have some large momenta. So a football player on the run is something that has quite a bit of momentum. And we can increase that momentum by increasing the mass. So you could have a train, something with larger momentum. A moving train weighs quite a bit in terms of tonnage and would definitely be harder to stop than a football player. But even more difficult to stop would be this comet hurtling towards the Earth. So again, we increase the mass, we increase the velocity, and we're going to have more and more momentum. On the other side of the scale is something with small momenta. So a toddler on a tricycle. Moving forward, this toddler has some momentum, but they're going to be easier to stop or slow down than the football player. And even easier to stop and slow down than the toddler would be this mouse on a wheel. Now, technically, this mouse isn't moving forward, and the momentum that we have is the rotational momentum of the mouse wheel. So that's a type of momentum, but the mouse itself, in terms of moving, doesn't have any momentum. And if you want to get down to just straight zero momentum, it's this P. So not only is this P very small, but because the P has no velocity, it's just sitting on the table, its effective momentum is zero. So what are the variables that impact momentum? Well, the first variable is mass. The bigger the mass, the bigger the momentum. And this is our linear relationship that we've talked about before. So if you double mass, momentum will also double. If an object has twice as much momentum as another object and their velocities are the same, then the mass will have doubled. The next variable is velocity, and velocity also has a linear relationship with momentum, meaning if you double the velocity, you'll double the momentum. So let's look at that equation. It's simply this. P, which stands for momentum, is equal to mass times velocity. And you got to make sure you put your units on there. We measure the mass in kilograms, so try to convert if you have something else, and our velocity in meters per second. So we want to convert our velocity to meters per second if they are other units at the time. And that's our momentum equation. Here are some trends. Number one, positive versus negative momentum. Well, you can't have negative mass. You can have a negative change in mass, but your mass number can't be below zero, otherwise there is no object to talk about. So if you want a negative momentum, that simply means that you have decided on a direction for your velocity, and if you chose it to be going in the negative direction, then your momentum will be negative. If something has a small momentum in the positive direction, it will have a smaller velocity than something with a large momentum in the negative direction. So just remember that positive and negative at the beginning of your answer just has to do with direction. It doesn't have to do with magnitude. The next idea is that mass and the velocity both impact momentum equally. So because they both have linear relationships, if you double one, it has the same impact as doubling the other variable. And we can illustrate this by showing some examples of objects with different momentum. So we've got large momentum, medium momentum, low momentum, and no momentum. So something that has large momentum could have a large mass and a large velocity, like our comet. A medium momentum can be a mix of medium mass, medium velocity, or you could have a small mass and a greater velocity, or you could have a great big mass and a small velocity. So, in terms of a great big velocity and a small mass, maybe think of a bullet. In terms of a large mass and a small velocity, maybe think of a train rolling slowly. Um, a low momentum will have a small mass and a small velocity, so maybe a pea rolling on the table. And of course, to have no momentum, you have to have some mass. But no matter what, if your velocity is zero, you have no momentum. So I want you to take a moment and flip to your summary section, right? And go ahead and answer the essential question, which is what are the relationships that contribute to the momentum of moving objects? And fill out your graphic organizers and extension questions as well. Thank you for listening.